So this is week 8. So I hope you guys look through the 4 videos. I asked you to. So let me show. So you should go to the share screen. These are the. So you should go to week 8. Week 8 of the. This is week 8, right? So there are 4 videos I asked you guys to look through. So the first one is on percentiles of normal, t, and chi-squared. The second is on definition of confidence intervals. The third is on one sample confidence interval. And the fourth is on 2 sample confidence intervals. So these are the 4 videos I asked you guys to look through. I hope all of you have looked through the videos. I mean, if you haven't, please go to YouTube or the other channel and please have a look through those videos, right? Right, now what I'm going to do as usual is I'm going to go through the stuff on the 4 videos quickly. And if there's anything that is not clear about the 4 videos, you can ask me while I go through the notes, right? Okay, so let me change the camera now. So I will. Here we are. Hope you can see this. Hope. So this is the first video I did, which is on the percentiles of the normal, student t, and chi-square distribution. So for the, I'm sure all of you know the normal distribution. This is the normal density. So the percentile is defined by this notation Z subscript alpha, which means the area to the left of the point, the area to the left-hand side, which is this area here, is equal to alpha. So the area to the left of the point is equal to alpha, right? So this denotes the point where the area to the left is alpha. Now you can also have a case like this, where this point here is denoted by z1 minus alpha by 2. So the area to the left of this is 1 minus alpha by 2. And this point here is z alpha by 2, which is which means that the area to the left of this point is alpha by 2. So this area is alpha by 2. And the area to the left of this is also is 1 minus alpha by 2. So which means that the area to the right of it, the area to the right hand side of this should be alpha by 2 too. So these two areas alpha by 2. So the middle area must be 1 minus alpha, right? Okay, so this and because of the symmetry of the normal distribution, z alpha by 2 is minus of z1 minus alpha by 2, right? That's because of the symmetry. Now this is a table for reading the, I don't know if you can see this. This is a table for reading the percentiles of the normal. I showed you how to do this in the video, so I'm not going to go through this. If you have difficulties reading it, just please look at the video or contact me. And these are some examples on how to read the table. So for example, Z 0.9, if you want to read 0.9, you go to the table and look for the one that is closest to 0.9, which is this one, right? So this will be 1.28 approximately. That's what you see, right? Okay. Now the student's t distribution is again a symmetric distribution, right? So this point here denotes the value to the left of which you have an area of alpha, right? So the area to the left of this point, that is this area here, the shaded area, is equal to alpha, right? And once again, you can have 2 percentile points. Excuse me. You can have this point and this point. So the area the area to the right of this point is alpha by 2. The area to the left of this point is alpha by 2. And the area between these two is 1 minus alpha. So in this case, the notation for this point is TA, comma, A is the degree of freedom, comma, 1 minus alpha by 2, because 1 minus alpha by 2 is the area to the left. And the notation for this is TA, comma, alpha by 2, because alpha by 2 is the area to the left, right? Okay. Now, once again, because the T distribution is symmetric, this is equal to minus of this, right? Any questions, guys? Please use the chat room as usual, okay? Any questions you guys have, please use the chat room, and I'm happy to answer all your questions. And this is the table for the T distribution. This used to read the percentiles of the T. And again, I did 3 examples. I hope you looked at the videos. So for example, if you want to find the percentile of T with 1 degree of freedom and probability 0.9, then you go here and you read 1 from the first column and 0.9 across the row. So you get 3.078. That's what you see here, 3.078, okay? And finally, the chi-square distribution. The chi-square distribution is not symmetric, as you know. So here, this guy here denotes the percentile of the chi-square distribution corresponding to an area of alpha to the left. So in other words, the area to the left of this point, this area here, is alpha, right? Okay. And you can also have two different points like this, where this point and this point, right? In between them, they have an area of 1 minus alpha. And the right of this point, you have an area of alpha by 2. And the left of this point, you have an area of alpha by 2. So this is denoted by chi-squared A is the degree of freedom. 1 minus alpha by 2 is the area to the left of this point. And this is denoted by chi-squared A, comma, alpha by 2, because alpha by 2 is the area to the left of this point, this area here, right? Okay. Any questions so far, guys? Please let me know. Are you okay? Are you guys okay so far? Okay, thank you. All right, and this is the table for reading the percentiles of the chi-square distribution. And I did 3 examples once again. So for example, if you want to read the 0.01 percentile of a chi-squared with 1 degree of freedom, you go here and you look for 1 along the first column, and then 0.01, which is this one, right? Okay, this is really small. As you can see, this is 0.000157, which is nearly 0, right? That's why you have this, right? Okay, so that's the first of the 4 videos I asked you to look at. The second of the 4 videos is on confidence intervals. So like confidence intervals are useful because normally, like if somebody asks you what's the, where can you find, sorry, I got a question from someone. Where can you find they are in the course website. Where can you find these tables? They are in the course website, yeah. Guys, if you go to the course website, you see the tables are there. The tables for the T, the tables for the normal, the tables for the chi-squared are all on the course website. Okay, confidence intervals are useful because, like, if somebody asks you what's the temperature right now in Manchester or wherever you are, it's normally it will be more accurate. It will be more accurate to say an interval estimate than just a point estimate. So that's why confidence intervals comes in. All right, so this is the definition of a confidence interval. 100 times 1 minus alpha confidence interval for theta is defined by this interval from L for lower, U for upper, and such that the probability that the theta lies between L and U is equal to 1 minus alpha. So So this is the definition of a confidence interval. And then confidence limits are the L and the U. So the L is known as the lower limit and U is known as the upper limit, right, of the confidence interval. And the next thing is the coverage probability. The coverage probability is the probability that theta lies between L and U. So this is known as the coverage probability. And the next thing is the coverage length. Coverage length is simply the difference between the upper limit and the lower limit. So it's U minus L, all right? Okay, you can find all this in the website. All this stuff are all on the course website, guys. All right, so that's the second video. The third video I asked you guys to watch is the one sample confidence intervals. That is, whenever you have a sample and you want to know, there are 4 different one sample confidence interval I talked about in this video. The first one is the confidence interval for the population mean when the population variance is known. The second is the confidence interval for the population mean when the population variance is not known. And the third is the confidence interval for population variance. And the fourth is the confidence interval for population proportion. So I'm going to take you through each of these. I mean, you've probably seen this video anyway. So let's take the first case where you want to find the confidence interval for the population mean when the population variance is known. Is this one, right? So here, I mean, if you did not follow this, please let me know. I mean, for the exam, I want you to understand the derivation of the confidence interval that I have given you here. So the confidence interval is the one in the bottom. This is the confidence interval. And to derive this, I use the following fact. You have a random sample from a normal with these parameters where sigma squared is known. Then one of the results that I talked about on the video on normal distribution, if you remember, is that the sample mean also has a normal distribution, right? If you have a random sample from this, then the sample mean also has a normal with these parameters. Now from this statement, this follows, and from this statement, this follows. And if you continue going through these steps, I'm not going to go through them again because I've done this already in the video. So I hope you've seen the video already. So if you follow these steps, then finally you will come with this statement that the probability that the mu is the population mean between these two is equal to 1 minus alpha. So hence, 100 times 1 minus alpha confidence interval for mu is this interval. This is the lower limit and this is the upper limit. Hello guys. So this is exercise on how to derive a confidence interval, guys. Is this clear or not? So this is I mean, if I ask you to reproduce this in an exam or in an exam, you should be able to do it by yourself, right? Okay. So this is the confidence interval number 1. Number 2 is when here we are looking for the confidence interval for population mean when the population variance is not known. So we assume the same thing as before, except the population variance is unknown. So we have this result from the video on normal distribution. Now from this follows. Now from this follows, because if you look at the video on the student's t distribution, yes, Vikram, yes. I mean, you can be asked to derive confidence interval that I have not taught you yet. I mean, that's why I will do examples at the end of this class. All right. So from this follows from this, and from this follows because of the video on the student's t distribution. And from this, you can write this. And finally, after going through several steps, you will get to this statement that the probability that mu, the population mean, lies between this guy and this guy is 1 minus alpha. Hence, 100 times 1 minus alpha confidence interval for mu is this, right? Okay, so I mean, you should do a few examples. You should do a few examples on confidence intervals. You will get to know how to do it, right? So that's why after finishing this, I'm going to do as many examples as possible to give you a flavor about how to derive confidence intervals. All right, this is the third one. So this is the confidence interval for population variance. Now, this starts from this statement here. This, I'm sure you've seen this before. You should look at the video on chi-square distribution. This is one of the results I taught you. Now, from this, this follows, right? And from this follows. And hence, a confidence interval for population variance is this one, okay? All right, so that's the third one. The fourth one is the confidence interval for population proportion. Now here we are assuming that we have a random sample from a Bernoulli distribution with parameter p. I'm sure you know from probability 1 that the population mean of a Bernoulli is p. The population variance is p times 1 minus p. So by the central limit theorem, which we talked about some time ago, this guy here should approach the standard normal if n goes to infinity. Now, suppose n is large enough, the sample size, so that this is approximately equal to this. You get this statement. And from this statement, you get this. And from this statement, you get this. And finally, after following all the steps, I hope you watched the video. I mean, after following all the steps, you will get to this. You will get to this, right? And what this says is the probability that the population proportion between these two is approximately equal to 1 minus alpha. So hence, this one is a confidence interval for the population proportion. Yeah, I got a question from Mikhail. A population proportion, like for example, suppose you're interested in the number of people who smoke in the UK, right? So in that case, what you're looking is the proportion of people. So you're looking for proportional people who smoke. So whether it's 50% of the population or 60% of the population or 30% of the population. So it's a proportion in a number between 0 and 1, right? I mean, there are many examples where population proportion is of interest. It's not just smoking. It's like, for example, number of people who own a television. So the proportion of people who own a television, or proportion of people who own a car, things like that. So proportions, happen every day. People talk about proportions all the time, right? Okay, so that's okay. So what I have shown you here, guys, is that this is a confidence interval for proportion, right? Yes, yeah, but Bernoulli, yeah, you always talk about Bernoulli when you have proportions, because like remember Bernoulli is a 0-1 random variable, right? So if you take the case of smoking or not, there are only two possible outcomes with smoking. Either you smoke or don't smoke. So it's like a Bernoulli, right? And there are only two possible cases with whether somebody has a TV or doesn't have a TV, right? So it's a 0 or 1. So Bernoulli is automatically, you cannot use Bernoulli if you have more than two cases. Bernoulli has only two cases. Either you have it or don't have it. Either you smoke or don't smoke, right? Okay. If you have more than two cases, then you cannot use Bernoulli, obviously, right? But proportion, normally proportion is for cases where you only have two cases, right? Like smoking or having a TV or having a car or passing an exam or things like that. All right, you only have two cases, right? Either you have it or not have it, right? Okay. All right, guys. Any other questions? So this is the confidence interval for the population proportion, right? All right, so this completes the third video. The fourth video I asked you guys to watch is the two sample confidence interval. So here you have basically you have two different populations, and you want to compare the means or the variances or the proportions, right? So there are, once again, there are four different confidence intervals. So the first one is for the difference in population means when the population variances are known. The second is the difference in population means when the population's variances are unknown but equal. And the third one is for the difference in population means when the population's variances are unknown and not equal. And the fourth one is for the difference in population proportion. Excuse me, you guys okay? Questions? Hello, guys. Anyone has questions? Sorry, I can't hear you, sir. Can you repeat? Okay, so these are the four confidence intervals, two sample confidence interval I'm going to look at. The first one is this one. So here you have two independent random samples from two different normals, and we are assuming that the population variances are known, right? In this case, and we are also assuming that the two samples are independent of each other. So let X bar denote the sample mean for the first sample, Y bar for the second sample, right? Now, you know from the video on the normal distribution that X bar has the normal with these parameters, Y bar has the normal with these parameters. So the difference will also have a normal with these parameters. Now, if you follow all these steps, after a while, you will get to this statement here. So this statement says that the probability that the difference in the population means lies between this and this is equal to 1 minus alpha. All right, so hence 100 times 1 minus alpha confidence interval for the difference in population.
Not muted.
So hence 100 times 1 minus alpha confidence interval for the difference in population means is given by this formula, right? Okay. All right, guys. So I'm not going through the steps in detail because I have already done that in the video. So I hope, I mean, if you did not understand the video, please, you can ask me now or you can ask me later by contacting me 24/7, okay? So this is the first of the four confidence intervals, right? And the second one, this is where you have two independent random samples, again from normal, but here they have the same variance, and the variance is assumed to be unknown. Is unknown, all right? In this case, I haven't given you the derivation. I don't expect you to know the derivation. In this case, it can be shown that the 100 times 1 minus alpha confidence interval for the difference in population means is given by this formula, where SP is given by this formula. It's known as the sample pooled standard deviation, right? Okay. Right, so this is the second. The third one is this one. So here, once again, you have two independent random samples. The first one from this, the second from this, and they are independent of each other. and here we are assuming that the population variances are unknown and not equal, right? And in this case, it can be shown, once again, that I don't expect you to know the proof, it can be shown that 100 times 1 minus alpha confidence interval for the difference in population means is given by this formula here, right? Where A is the degree of freedom given by this complicated expression. Sx squared is the sample variance for the first sample, and sy squared is the sample variance for the second sample, right? Okay, so that's the third of the four confidence intervals. And finally, this is the final confidence interval. Here you have two independent random samples from two different Bernoulli, right? So Px denotes the population proportion for the first sample, Py denotes the population proportion for the second sample. And here we have a confidence interval for the difference in population proportions, right? And it's given by this formula. Once again, I don't expect you to know the proof of this formula, just how to apply this formula. I mean, this kind of confidence intervals are useful because like if you take the example of smoking, which I talked about earlier, right? Like if you look at the proportion of people who smoke in the UK who are male and the proportion of people who smoke in the UK who are female, and you want to compare them, you want to compare whether the proportions, how the proportion of smoking differs with respect to gender. So you have one proportion for male, one proportion for female, right? And you want to see what the difference is like, right? And you can use this formula to find out the confidence interval for the difference in the proportion of smoking for male and female, right? Okay. All right, guys. These are the four videos I asked you guys to watch. I hope you did watch these four videos. I hope you guys did watch it, and if you did not watch it, please go back and watch it, guys. Right now, what I'm going to do in the remaining time is I'm going to do as many examples as possible. All right, the first example. The first example. I should call this example. I don't know why I called it example 5, but I should have called it example 1. This should say example. Oh, I don't. let me start with something that is. Let me start with the easy example. Let me start with this simple example because I don't want to start with something which is complicated. Okay, so all right, let me. Sorry. This is example. Example 1, right? Okay. Suppose okay. So all right. So here you have a random sample from a log normal. Assume excuse me. You assume you know what log normal is, right? Log normal with parameters theta and 1. And the question is to find 100 times 1 minus alpha confidence interval for theta, right? Now, you know that if xi is log normal with parameters theta and 1, one of the properties of the log normal is the following, that the log of xi will be normal with parameters theta and 1. Do you know this?
We haven't heard of it. If you could briefly explain it to us, I think that'd be great.
Anyway, this is a property. I mean, this is a property. I thought I talked about this before the Easter break. Anyway, if you don't know this property, just try to remember this, all right? If you have a random variable that is log normal, then the log of that random variable is normal with the same parameters, all right? That's all. That's all I expect you to know. ln stand for log normal. Sorry, ln is abbreviation for log. It's an abbreviation for. I'm not well. I don't. It will not be required for this course, but I don't think it will be in the exam. I don't think so. But it's a simple distribution. I mean, I think it's in the list of. You should go back to the website and look at the distributions. You will see that log normal is one of them. Right? You should, I don't know. You should guys. You should, I'm sure you know where the website is, right? You should go to the website and look at the right at the beginning. There's a list of probability distributions. There's a PDF file that contains that, and if you look at it, you will see the log normal is one of the distributions listed in that PDF file. Okay. All right. Anyway, let's move on. Okay, so log of xi has this distribution, so which means that the average of the log of xi right will have a normal distribution with parameters theta and variance 1 over n. Okay, so that's by property of the log norm of the normal distribution I talked about in the video on the normal, right? So this implies that okay, and this implies that yeah. Now you can write this as, if anything, I mean, log normal is just like any other distribution, guys. It's not like, just try to remember the fact that if a variable is log normally distributed, then the log of that variable is normally distributed with the same parameters. Right? That's all you need to know. It's not something complicated, you know. Okay. All right. So from this, you should be able to follow this from what I've taught you in the normal distribution, right? Okay. Now, to find the confidence interval for theta, I'm going to use the following argument. Because this guy here has the standard normal distribution, the probability that Okay, right. Okay, now what you need to do is to rewrite this statement as a statement on theta. Right now, what you have here is not a yeah. You can do that. You can do that. You can do that, Vikram. Yeah, that's another way to do that, Vikram. Yeah, you're right. All right. Now, anyway, let me rewrite this as a statement on theta. So what I'm going to do is, first thing, I'm going to divide everything inside the probability statement by root of n. Okay. You see what I've done? All right. The next thing I'm going to do is I'm going to take this guy here to over here and to over here, right? So so in other words, subtract this term out of each of the three terms. So you will get the following. You will get okay. Are you with me, guys, so far? Let me know. If you don't follow, please let me know, guys. Okay. All right. And finally, what I'm going to do is I'm going to multiply every term within the brackets by minus 1, right? And if I do that, this is what you will get. If you multiply everything within the brackets by minus 1, sorry, this shouldn't be, sorry guys, this should be greater than or equal to, not less than or equal to. Okay, this is what you will get. All right. So hence, the conclusion is the following. That the conclusion is this is the lower limit, and the upper limit is this one. All right. Is this example clear or not? So this is an example on the log normal. Well, because the reason that we introduced the sum part is because we need to use all the data. You see, there are n data points, right? And there are n data points. So if you go back to the beginning, right? If you go back to the beginning, there are n data points. So we need to use all the data. So one way to use the data is to use the fact, since log of xi is normal, we know that from the stuff that we did on the normal distribution, yeah, that if something is normal, then the sample mean is also normal, right? So since log of xi is normal, then the sample mean of the log of xi, which is this one, is also normal with the parameters theta and the variance 1 divided by n, sigma squared divided by n, which is 1 over n. Yeah, you can. Yeah, Alex. Yeah, you can, Alexandra. Yeah, you're right. I mean, you can simplify this further. If you like, you can simplify this further by changing this guy here. Remember, by you can replace z alpha by 2 by minus of z1 minus alpha by 2. So this guy here actually can be changed. This is the same as thank you for pointing out, Alexandra. So this is this is the same as the following. Okay. Now, if I change this to by symmetry, this is the same as minus of this. So it will become minus minus, which is plus. Okay. You don't understand what next to z. I mean, which one do you mean? I mean, I don't understand your question, doesn't. The third line before the end. This is okay. This is alpha by 2, madam. This is alpha by 2. This is 1 minus alpha by 2. I mean, sorry if my writing is not clear. My apologies for that. So this is alpha by 2. This is 1 minus alpha by 2. This is 1 minus alpha by 2. All right, guys. Any other questions on the first example I did today? I don't know. I was gonna do many examples today, but it seems. So this is example 1. Let me see if I can do just one more example before the end of the day. All right, just let me try to do one more example, okay, before I. So this is example 2. I will do more examples next week, but let me try to do one. Now, suppose Okay, so this is example number 2, guys. So this is the CDF of a distribution which has parameter b, and we want to find the confidence interval for the parameter b. Okay, now the way to do this is you want sorry. Oh, excuse. I think. Okay. You want the probability that the variable you want the probability that x is between two numbers, right? Right, to be equal to 1 minus alpha, right? Okay, and let's call this number, say, let me call this number, say, P and Q, right? Now, one way to determine these numbers is so that, I mean, suppose one way to determine these numbers is as follows. Okay, suppose the density looks like this. So you want two numbers, P and Q, so this is your P, this is your Q, so that the area between these two, excuse me, I think something, the area between these two is 1 minus alpha. Are you guys able to see the video? Hello? Okay. Now this one, that means the area glitch. Yeah, I know there's some problem with the video. I don't know why. So if this area is 1 minus alpha by 2, then you can take this area here to be, I think I'm running out of time. You can take this area to be alpha by 2, and you can take this area to be alpha by 2 too, right? So, okay, so to determine P, you need to solve the equation, the probability that x is less than P or less than or equal to P is alpha by 2, which is the same as saying that yeah, and it is same as this, and this is the same as this, and this is the same as saying that P is equal to minus log of okay, right? Now to solve for Q, you need to solve the equation that the probability that x is less than or equal to Q is 1 minus alpha by 2. And if you follow the same procedure, right, you will get Q equal to minus log of 1 minus alpha by 2 to the power 1 over b is equal to, so this is what you will get, right? I'm sorry for the focus problem with the video. I don't know why. I don't have the most advanced technology here. So this is your P, this is your Q. So the probability that x is between equal to this, right? Yeah. Now, what you need to, no, I have run out of time. So what you need to, I don't think I've, now what I want you to do is to solve, rewrite this equation, rewrite this as a statement on B, right? And that will give you the confidence interval. That will give you the confidence interval for B. You shouldn't be, I mean, with all the math you have done, guys, you shouldn't find it difficult. You shouldn't find it difficult to rewrite this as a statement on B. You see what I've done? I drew this picture just to make it clearer that these are the 2 points P and Q we are looking for. And we are looking for an area of 1 minus alpha between them. So this area could be alpha by 2, and this could be alpha by 2 too, right? Okay. Now to determine P, you solve this equation. To determine Q, you solve this equation. And this is what you get for P, and this is what you get for Q, right? So we have the probability statement that the variable X lying between these two is 1 minus alpha. Now we need to rewrite this as a statement on B because that's what we are looking for, Mikhail. Because we are looking for a confidence interval for B, right? That's the question, right? So if you rewrite this as a statement on B, you get the answer. Because I have run out of time, I would like you to do this, please. I'm sure it's easy peasy for you, you know. All right, so we got a tutorial right now. Yes, you're right, Don Hin. Yeah, Don. I mean, yeah, yes, you need to write it as a statement on B, Don. Yeah. We got a tutorial at 11 a.m. UK time if you're in the UK. So please do come to the tutorial if you have time. I will be taking the tutorial right now in about 6-7 minutes time. So about 7 minutes time, I will go through the tutorial. Okay. Anyway, any questions on the? I know we had some issues with the video and so on, but are you guys okay with the lectures, with this session? Anything you like to ask, please let me know. All right, guys. So I will see you in the tutorial in about 5 minutes or 6 minutes time. I will see you, right?